We're going to move on from multiple regression to the one-way ANOVA. And ANOVA stands for Analysis of Variance. And from this point on, I just want you to kind of keep in mind that most advanced statistical techniques beyond multiple regression are refinements upon multiple regression. So remember that multiple regression it's the kitchen sink of statistics. We can put in just about any potential variable we want to in some form or another. We can create interaction terms. We can create dummy codes to allow us to look at categorical variables. We can look at nonlinear trends, and all of these are the potentials that we have with the multiple regression. However, many of these are kind of workarounds, and many of them include basically additional variables. We're creating variables out of existing variables, and every time we do that, we're making a more and more complex model, and we're making a less powerful model. And again, power is power is whether or not we can detect an effect that is actually there. So the more complex the model, the lower the degrees of freedom. The lower the degrees of freedom, the larger the critical value has to be for that statistical test to be considered significant at a p of 0.05, which also means that as we add these workarounds, for example, if we've got a categorical variable with 5 levels, we're going to have to create multi-dummy codes. And every single one of those is adding to the complexity of the model. It's adding variables to that model. And it's making it to where we'll have to find a larger effect for us to be able to claim statistical significance. The reason I want you to kind of keep in mind just broadly how multiple regression works as the kitchen sink of statistics is a lot of the advanced statistics that we're going to talk about past this point are either focused versions of a multiple regression that are made to handle a specific situation that is common in the research sciences in a way that allows it to look at it with more power. Basically allows us to use less variables to test the same statistics, and therefore less variables, more focused, more powerful. That doesn't mean that we're cheating. That means basically that the multiple regression is kind of clunky in how it looks for things. So we can actually adjust for that and create statistical techniques that are more accurate to our p-value, our chance of being wrong, our percentage chance, our proportion that we are incorrect in our assumptions, and still allow us to look for fairly complex relationships. The second type of advanced statistics that we're going to talk about more next semester are ones that actually allows us to look at multiple outcomes, because everything we're talking about this semester is still what's considered a univariate statistic, as is the one-way ANOVA. It is a univariate statistic, and that single statistic, that single variable, is referring specifically to the outcome. So a univariate statistic can be incredibly complex with its independent variables. We can have a multiple regression with 10 plus predictors, but what makes it a univariate statistic is we're still looking at a single outcome. So this set of audio slides is mainly going to be looking at the introduction to ANOVA. We'll then have a set looking at computing the ANOVA. We'll then have a set looking at post hoc tests and why we need them. And finally, we're going to talk about contrast and trend analysis, which is kind of an interesting thing that we can do. It's a little less commonly done, but it does allow us to look for nonlinear trends in our data or linear trends in our data when we're looking at categorical variables. And we would only do that if we actually have a reason to look for that. So kind of contrast and trend analysis is kind of bringing the ANOVA back to its multiple regression roots. So for this set of slides, though, let's just talk about the ANOVA itself and where it came from. So the father of the ANOVA is Ronald Fisher, one of the greats in statistical techniques. He was an English evolutionary biologist, geneticist, and statistician, and he lived from 1890 to 1962. Was probably one of the most published statisticians of our time, or ever. 395 published articles, all of which, for the most part, had an enormous number of citations. So Ronald Fisher had a major impact, not only on his field, evolutionary biology and genetics, but also in the field of statistics, and through statistics, through actually almost all other scientific fields. He created the ANOVA as a way to take the multiple regression, which, as I said, was very good for looking at correlational relationships, looking at existing data, But what Ronald Fisher noticed is a lot of times what people are wanting to do is categorical research, looking for differences between groups of people or groups of interventions. And that as such, the multiple regression was not a very powerful design when you had to do those workarounds to use it to look at these situations. Therefore, he wanted to create mathematically a multiple regression model, if you will, that is actually set up and standardized to look at categorical relationships. So we're specifically going to start with the independent measures ANOVA. And an independent measures ANOVA means just that. It's independent measures. In other words, we have a independent variable, and in this case, we're talking about a simple ANOVA or a single ANOVA. So we have a single independent variable that is categorical with 3 or more groups. And those groups are independent. They're not affecting each other. They're not the same people. They're truly different groups of people. So this test is used when your design meets the following criteria. It compares more than 2 groups or treatments, and it uses different subjects for each condition. So in order for us to use an independence ANOVA, we need a categorical IV, which is 3 or more conditions or treatments or groups, and that those people in each one of those groups are different and are not affecting each other. In other words, their scores are independent. So this is especially useful when you have access to a larger sample size. So do recognize that as each group you add increases the number of participants you need. So if a minimum number, a rule of thumb for the minimum number of people for a t-test is approximately 10 per group. So if you're running a t-test on 2 groups, you need at least 20 different people. With an ANOVA, if the minimum is 3 groups, you need at least 30. And if it's 4 groups, 40, 50, 60, etc. And again, that rule of thumb of 10 per condition is pretty much a minimum and still not particularly powerful. I honestly suggest that a better rule of thumb is at least 20 participants in every one of your groups. So you usually need a larger sample size. You may also be using this because you're not able to test and retest the same people, or you may be worried about order effects and maturation and carryover effects. So all of these would be reasons to look at this particular methodology. This is also probably one of the more common ways that we actually do experimental research in the social sciences and specifically in psychology. So looking at the differences between groups of people or exposure to different treatments to figure out which treatment works better is kind of a cornerstone of psychological research. So again, the ANOVA is the analysis of variance, and it allows us to compare more than 2 groups at one time. Now, we could just simply run a series of t-tests. So we could be comparing, for example, if we had 3 different conditions, 3 different treatments, 3 different groups, we could compare group 1 to group 2, that's a t-test. Group 2 to group 3, that's a t-test. And group 1 to group 3, that's a t-test. We could run 3 t-tests. The problem with this is that each one of those t-tests would be being conducted in isolation. In other words, it doesn't know that we're running other t-tests. And again, remember that one of the most important pieces of information that we're gathering for a statistical test is what is the actual type 1 error rate. In other words, what is the chance that we're wrong? And every statistical test basically exists in a vacuum. It assumes that you're not running any other tests. And as we all know, if you flip a coin over and over and over again, every time you flip that coin, there's a 50-50 chance, assuming the coin is not rigged, that it'll come up heads or tails. However, we all can pretty much put together that if you flip a coin 5 times, you're unlikely to get heads every single time. And that's the problem with running multiple tests, is that each individual test is still, if it's a p-value of 5, that means or 0.5, that's a 5% chance you're wrong. And the next one, 5% chance you're wrong. And the next one, 5% chance you're wrong. But taken in total, the chances that one of those combined is actually inaccurate is greater than 5%. So it inflates the type 1 error rate. So that's the first reason that we want to run an ANOVA, is we want to run a single omnibus test. And you're going to hear that term a fair amount. An omnibus test is a statistical technique that initially starts with a test of everything that's going on in your data set and creating a p-value based on that. In other words, it says, is there a non-inflated type 1 error, 95% chance of certainty, that something in this data is going on, which then allows us to go in and look to find out where is that thing going on. Where are the differences? Is group 1 different than group 2? Is group 2 different than group 3? Or maybe group 2 is the same as group 3, but group 1 and 3 differ. We don't know, but at least we know that overall, within this data set, we have confidence in that initial p-value. Also, the same problem with just running multiple regressions is that because the multiple regression requires us to create dummy codes, we're in that same boat again of, and we're not going to inflate the type 1 error test because, again, multiple regression gives us an omnibus test. But what happens now is that it's an inelegant way to look at it, and it is a less powerful way to look at it. There are three main types of ANOVAs. The first one, which is what we're talking about today and this week, is the between subjects ANOVA. Every individual group or treatment has different people. There's the within subjects ANOVA, which we'll be talking about next week. The within subjects ANOVA specifically is looking at, it's basically a repeated measures design. You still have 3 or more conditions or 3 or more quote-unquote groups, but it's the same people in all of those conditions. And finally, probably the more interesting and intriguing ANOVA that we'll be talking about later this semester is the factorial ANOVA, where we have multiple IVs and we're looking for interactions. So for today, though, we're going to focus on that one way between subjects ANOVA. And one way, again, means one IV. So the outcome variable, the properties, these are kind of the assumptions. The outcome variable has to be continuous. Again, it must actually be a scale in either ratio or interval. The predictor is categorical. There is no limit on the number of categories, commonly known as conditions, groups, or factors, depending on who you're reading. Just recognize, though, that as we add categories, as we add factors, as we add individual groups or individual conditions, we are decreasing degrees of freedom. In other words, an ANOVA with only 3 conditions is going to be more likely to find a difference that's there than an ANOVA with 4. And likewise, an ANOVA with 4 conditions is going to be more likely to find differences and tell you that they are statistically significant than an ANOVA with 5 conditions. So what the analysis of variance initially does is it computes a ratio, F, from different sources of variance. And F in this case is our statistical test. It's what we're calculating. So where a t-test is a t, a correlation is an r, a multiple regression is a series, but usually we're looking at beta. In this case, we're reporting F. And again, that's a capital F, and it is italicized. And basically what we're looking at with the F is the same thing that we've been looking at least theoretically, in all of our statistical techniques so far. It's the total variability in your sample. Everything that was found, all variance in between your conditions, within your conditions, and whatever you measured, your outcome. But it's trying to partial that variance until a top of the equation and a bottom of the equation. So the first thing we want to look at is the between group variance, variance that measures the differences between the conditions. This is the effect size, the difference between means, and we want that on the top of the equation. So the larger that is, the stronger that effect is, the larger the top of the equation is going to be, numerically. The bottom of the equation is the within group variance. It's the remaining variance. It's error. It's the measure of differences within each condition. So not looking at the differences between the conditions, but just looking at the total variance within each condition. And again, it's generally a measurement of error, and we want that as small as possible, and that goes on the bottom of that equation. So we are testing the between groups differences. If the treatment is effective, the between group variance will be large. The top of the equation will be the larger number. The within group variance comprises several sources of error, individual differences both within and between, and experimental error, inaccuracies, inconsistencies, measurement problems with the variable. So think about this. If you have a 5-item measure, so this is your outcome, this is your DV, and it's 5 individual Likert items. So a Likert item is basically a strongly disagree to a strongly agree on a 5-point scale. And people take this measure, they take the 5 items, and at the end you collapse that into a single score. But when you look at the actual alpha, the internal consistency of those 5 items, you find that it's acceptable, 0.72, which acceptable internal consistency ranges from 0.7 to 0.8. But that also means it's not perfect. It's a little inaccurate. It's not super tight in its measurement of one thing. There's some inconsistency in there. That means that even if you're getting close to the true score, people are going to be varying on how they respond to those 5 items based on something beyond just a measurement of what you're actually after. There's already some error in that measure. And that error is going to show up at the bottom of the equation. And it's going to show up by greater variance in people's scores, especially across those items. Now, let's continue this thought exercise. And in this case, we actually take a measure, again, 5 items, Likert scale, but this one has an internal consistency of over 0.9. So it is highly consistent. Those 5 items are very related to each other. They seem to really all be measuring a single unitarian construct. You're also going to find less variance then across scores within each group because you're getting closer and you can actually quantify it at this point to an actual measurement of what you're after. And therefore, the experimental error in this case is going to be smaller. So anything you can do to increase the accuracy of your measurements and to also reduce any inconsistencies between your groups other than what you're manipulating is going to reduce that error at the bottom of the equation. So to maximize the treatment effect and reduce error, in other words, to try to make sure we set up a study that is likely to find an effect if it is there, we want to basically really make sure that the effect size that we're looking for is something that is findable and is going to be a fairly large effect. And we want to be very careful that we set up the methodology of the study to make sure that we are very consistent in how the measures are given to all subjects, that we are very conscious and cognizant of the type of measure we're giving and its reliability and consistency, and that we are very consistent in the treatment given to the subjects in each group. So if a treatment is being given, let's call it treatment 1 in group 1, we want to make sure that everyone in that group is very much the same in how they get that treatment. All of these methodological techniques are going to help us knowing the equation that we're going to run once we're done collecting our data. We want to make sure the bottom of that equation, the part that measures just variance, just error, just differences between people that have nothing to do with what they actually are responding to in your study, we want that as small as possible. And our measure of the differences in those groups based on our treatment, we want to be as large as possible.